Hello and welcome to the VEST webinar series. I'm Frank Newsom, your moderator for today's webinar session. And today we'll show you how MDTools can be used to design custom inlets, outlets, or midsections for sectional valves. This webinar will last approximately 45 minutes. You'll be able to submit questions or comments at any time during the webinar by posting in the questions section located within your webinar control panel. Questions may be answered as they're posted, or we'll try to address them in the last 5 to 10 minutes or so of the webinar. Note that today's session is being recorded and that the audio is muted for all attendees. If you're experiencing any technical issues, please use the chat window to alert our support staff. Now it is my pleasure to introduce our speaker for today's webinar session, Carlo Molon. Carlo has worked in the hydraulics industry for many years and currently manages application sales and training for VEST desktop and cloud products. Carlo?
Thank you, Frank, and thank you all attendees for joining today's webinar. So today I'll try to design a custom mid inlet for a sectional valve. Well, it's basically a mixed application. On the left, we'll have three compensated proportional section working section, and on the right we have a couple of modular NG6 subplates. So I took some sample products. So I had a 3D model for a Bosch Rexroth sectional valve. So today I'll use this working section. And on the right, I have a Eurofluid subplate. So those are three tie rod elements normally used in small power packs industrial application. I'll try to make a small exercise explaining how to efficiently design a custom mid inlet serving these two elements. So one sectional valve and on-off subplate. I also draw a small end plate just to cover the left side of the Bosch Rexroth working section. So the diagram is pretty simple. So we have a pressure entering. Since the sectional valve has all compensated elements, I don't need any pressure compensator, while I put a pre-compensator for the right elements with a flow restrictor and a relief valve and a shuttle valve that will select the load sense signal from the right and from the left elements. So my mid inlet will be the following. In terms of design structure, so basically I'll draw my manifold in between. I will have my working section on the left for the Bosch Rexroth elements, and on the right I will have the Eurofluid subplates. My P and T will be here on the front face, P and T, and then I'll put valves on top face. Some consideration normally when we do this kind of exercise. So since if I look frontally at this block, if I have the working section here, normally the element, we want to limit the height of the element, not to go below the element of the working section, because usually we have end plates on both sides, so we don't we want to really fix the assembly on the bottom part. So my constraint will be that the bottom part of my custom inlet will be almost on the same line as the working section. So here I will have my P and T port. Let's start the design. To make it faster, I have already made the diagram in Hydro, and I'll use my export to MDTools from Hydro. Just a quick information. In these cases, you may not have ports PLST. So let me just for as an example, delete the LS, P, and T. So in order to have efficiently the export to MDTools from Hydro, in this case, we consider this element as really an interface fitted to the block. So this element in the Hydro Property Manager will need to have a cavity name. So I put the name of L8581 EDCP1, and which is the element that I'm using on the left. And this cavity name corresponds to a footprint I have made in my MDTools library. So one of the coming webinars will be about managing MDTools library. So there maybe I will show how to build this this section, this kind of custom footprint, just to show you a bit. So that's my MDTools library, and this is the custom footprint I have built that I will be using today. So it's a 3 tie rod elements with pressure, tank, and load sense signal. Similarly, I have built in my library the footprint corresponding to that Eurofluid valve, which I call Eurofluid 3 tie rod. And here is the footprint. So PT and 3 tie rod. This is a known load sense system, so the load sense will be added in the inlet section, like I showed in the diagram. In order to make this element be recognized with MDTools, we need to add ports. So the easiest way to add a symbol port to a symbol is by using the symbol port command. By selecting the symbol, we can define the port name. So I use the P port and selected the node. I do the same command to add the LS port and select the node, and similarly I do again for the tank port. So of course, now that I made this, it will be possible to make connection lines. As you see, there is the green dot showing the connection line. Similarly, I will be able to do it. You should not need to do again the connection line because they are there. Sometimes it's needed to regenerate the drawing. So that's an AutoCAD command, type regen, and it will regenerate the connections. So 2 commands before going to MDTools. We'll do a network. So we click net, select the manifold we want to design. Well, of course, the same happens for my right side. So here I have an element connected with PNT, and there is a name for the cavity footprint, EF3TR, like I showed in the library. I'll do a network command. So this command, I had already run it, so this warning says that something has changed because I have added new ports. So I just click OK and regenerate the networks. So this command will be able to identify networks in the block. I had already run it, so the naming are meaningful for me, but you can rename networks the way you want. So P1, the tank line, that is, let's call it P1, P2, and so on. So load sense 1, and so on. We can click OK. And when doing this network command, we also have the ability to verify a bit the connection that we have made. I forgot to mention, if you have any questions, just feel free to post. I'll be able to read them and try to address during the demonstration. Another small information, well, in this case, I've used some a mix of HIDAC valve. So this is a relief valve for a HIDAC, DB10P, pilot operated relief valve. And I have also linked a 3D model because I want to showcase the automatic assembly in MDTools. And similarly here, this is a HydroForce needle valve, and this one is an HydroForce logic element, and that's a small shuttle valve. Let's start. MDTools, selecting the envelope only, press enter, and this command will give warning in case some connection are missing. In this case, it's reflecting A and B ports that are not connected, because this command is now considering element 5 and element 2 as part of our assembly, but they are connected outside to our system. So this is not relevant, and we can skip it. Now, this is not a very complex system, although in mobile applications, sometimes even if the diagram is simple, then the complexity in the design are different, because sometimes it's easier to do industrial manifold rather than mobile manifolds. On the left, we have a list of the components. So item 10, item 9, item 2 is the left element. And although it is possible to define constraints, really, I don't need much time here for set constraints, because I'll jump. I have everything under control. I know exactly where to position the components, and then the rest will come. Again, we can look at networks. When we click a net, we can review if we made properly all the connections. When we are ready to design our block, we just click export and save our custom inlet. So this command will generate an XML file that contains the information for designing our manifold. And so now we really can forget the diagram, because the diagram is stored digitally into the XML file that we have generated. So today I'm going to use MDTools 790 for Inventor, the latest version that we have released. So let me jump to Inventor. You may know that we have MDTools on both SolidWorks and Inventor. 900 series is the SolidWorks one, 700 series is the Inventor one. So I'll jump to MDTools 790. Some configurations in the settings. Well, this version has a SQL database exposed, so I'm using a SQL library. In this week, we had some customer reporting issues with access databases on MDTools and Hydro. So if you are interested in getting rid of those issues, please remember we have a SQL technology for both Hydro and MDTools. In this case, I'm not going to use what I normally use, which are BSP plugs. I'll use expander plugs. I want to keep the block as compact as possible, so I'll select a decent range of expander plug. That's it. So in my design, I'll use expander plug. This section does not prevent you from using other type of plugs, but it's very handy, because this list of elements will then be available from the export command on the ribbon. Since I have my diagram ready, I will import it, Hydro schematic. Click on the three dots and load my MDTools webinar custom inlet. And nothing wrong was found. Actually, one possibility was that the cavity name was not recognized. So if a cavity is not there in your library, you will get a warning, and MDTools will ask you to map a cavity from the diagram with a cavity in the block. This is not the case, so let me start my block, and I'll take maybe 100 by 100 by 100. Well, this is not really smart. Usually, if you start with a 100 bar, you may use 99 by 99 by 99. That's more. Because you want always to have squared faces. So normally, manufacturer will always remove a bit of material from all sides of the block. So like I said, on the left, I want to have the Bosch Rexort elements. So I take my element 2, insert and position here. The position is okay. So since the block is 99, I'll use a 49.5, 49,5, and the position. So in this case, I help myself with the outline. The outline is really showing the dimension of the working section. So I go slightly below, so that I'll make sure that my block will be slightly over the bottom plane of the assembly. When I place my component, I have my engraving. I don't really need to engrave anything on this face, so I'll remove my engraving. But color show me really how the networks are made. So the light blue is the tank. So I want a tank port on the front face. I put it somewhere here and maybe in this position. And while I'll add a P port somewhere here. These drills are very large, so let me just reduce them a bit. So I shorten them 24 by 25. And I do match properties, copy the same drill depth here. So they are identical. With this P, I will need also to feed the other elements which are on the right. So I'll add also my side elements on the right, and I'll position randomly. So I can see with colors, so the tank line is here. And I'll start to do some connection. Well, the red connection is very easy. I'll add an offset hole to my P port. I'll take maybe a 12 millimeter diameter. The offset hole will be slightly on the y direction, -2. -2 is okay. And I can just stretch my drill and go here and make my connection. MDTools has connection check functionalities. So when we do a connection check, we can verify also the quality of connection. So we can see that this connection is not well made. The drill is short. And as you can see, it is also highlighted in the poor connection list. I skip the other checking because it's evident we have not connected anything in the block. So those unconnected ports reflect what we have not yet made in our design. But I want to focus now on the quality of this connection. 68%, it's not correct. You can fix manually as you want, or we have a command to fix automatically, which is the check band. Check band will study all the intersection and will try to fix them for you. In this case, I'll just move my drill slightly down a bit to make it more concentric. Now, my system has also the compensator, so I'll try to fit now to start fitting my components. I place randomly in the cavities and see. VC12 -3 is the pressure compensator. So I put it on this face and see how it works. Okay, so as you can see, well, the red connection is not bad. I'll just add maybe a couple of millimeters here, 105. I want to connect this orange with the orange, port number 3. And the connection is good. I also can stretch my P port directly to the port 2. And when you do stretch command, it's not always optimizing the drill. So if you stretch up to, then you may need to extend a bit the drill. Let me make 60 millimeter depth. When you see these graphic artifacts, just click color again, and MDTools will recolor all. There is a mode to always recolor the block. It's under settings, cavity color. It's refresh color all cavities, but I strongly recommend not to use it if you do large blocks, because every command will recolor all the block, and when there are hundreds of cavities, this may slow down performance. So I accept sometimes having artifacts, and when needed, I just color the cavity, and this will solve. I add an offset hole also for the tank line, 12 millimeters again, -5, and I want to stretch it. Since I'm very close to the face of the manifold, I use an incline drill, so I'll do stretch. At this drill, I'll stretch with inclination up to here, and maybe I just do a 5 degrees inclination, which is good. In order to make the other tank connection, I'll add a couple of plugs. So I'll add a construction port on tank, and I'll take 12 size on this face, in the center, and I'll move slightly here. And when you add the expander, you always need to pay attention to how far they are from the edge of the block, and also how far are from other expander plug. This is a tank line, so there will be no pressure, so it's not really critical, but in case, just use the measure command and check the distance, minimum distance. It's important to pay attention because expander, well, I prefer really to use threaded plugs, but I know that for compactness in mobile hydraulics, people use a lot of expander, but really you need to pay attention to where they are positioned to prevent failure or leakage. Similarly, I copy my plug and use and do the other connection here. So like in this case, this is not good at all because it will not be possible to fit this expander. So I'll add some material here. So I stretch my face and do a 105 millimeter. When you stretch material, the block, the drills will change in length, and again, like in this case, it's better to add a few millimeters again, and also on this direction. In this case, I can align these two cavities. Center to center intersection is always better when possible. So in this case, the drill is not well centered, so I'll just add slightly, maybe 8 degrees inclination, and that's it. Now the pressure is entering, and this is the P port for the Eurofluid subplate. If you don't know the port names, it is possible to show. This is not something I daily use. Well, actually, I show only during training and during demos. There is a command slightly hidden. It's called cavity ID. It is possible to show maybe port application name is what I want to see here. Port application name on all the faces, or you can just select a couple of faces. In this case, you could say left and right. When you use this command, please remember to use a larger font because usually the default one is too small. Maybe 28 is okay, and update. So in this case, as you can see, there will be a PT PNT. So you will be able to see corresponding to the drills the port name LS. I don't really need. Well, later I'll switch them off, but in this case I need to connect the P port with the same line, with the blue line. Let me add a construction port here on the top face. And I add another construction port here on this position. And I will simply copy and add another one. Well, we can try to see if we can make an incline drill, stretch this with inclination up to this with inclination. It is possible. The risk when you do incline drills is, like in this case, it's the maximum drill that you can accept. MDTools will do a validation for you. So the cavity, so let me show where this information is coming. That's the P port. It's a 10 millimeter diameter, and the maximum drill diameter is 10, defined by the manufacturer. So when you incline, the ellipses will be larger than that diameter. This warning will give you an idea of what is the maximum diameter that you can make. 8.9, so let me make 9 millimeter, and that will be acceptable. Let me also reduce slightly the angle so I can get rid of a plug. This logic element has the pilot on the port 1, so really we don't need a large drill for the pilot. We'll just use a small, so let me create a construction port on port number 1, and I need just a small 5 size. on the top face, and we can see a preview. The position looks okay. Let's check what else is missing. So if we do a connection check, now MDTools will give us an idea of what is wrong and what is not. So we have a broken net, so the load sense is not connected, and this is correct. We have a poor connection, and it is clear. We will extend the drill. A technique could be also making an inclined drill. So let me show you. We could make maybe a 5 degrees inclination, 8 degrees inclination, and go to the center, 0. When you drag the tip, pay attention, because if you don't lock the rotation, then you will be able to really, with freedom, rotate the drill. It is really out of control. So it's better to say 0, fix it, and then you will be able to stretch the drill, just changing the beta angle. But it's much easier to just type an angle, fix also that, and then you will be able to stretch only the depth. This is a common technique. This is doable. Again, we have the verification of maximum drill diameter. In terms of manufacturing, this can be a problem, because as you can see in this phase, we have inclination going up and going to the right. So if you have a 5-axis machine, you will be able to do it without any issue. If you have a 4-axis machine, this will require an additional setup, which may cost a lot of money. So pay attention when you do inclined drills, because you should take into consideration also which machine will be used to make that particular block. Okay, so we miss a couple of valves. So we have the relief valve, which probably can fit on the top face. And once in the top face, let me save my block. That's my custom inlet. I'll do a connect cavity. That's good. Then we need to connect the tank line. So now the tank is down there. So let's try to fit, to find a spot here. So I want to move multiple. I want to move all these cavities on this side. Now, the choice to make this inclined drill may not be that great, but let's try. We'll probably need another plug, but let's first find a solution. Designing a manifold is always a hit and try. You find a solution, then you change idea because you find a different path for the design, for other complexity in the circuit. So let me put a plug here on this side, and I copy the same plug on the top face, connecting with the tank line and connecting also with the other plug, and the position will be somewhere here. So this is a case where you need to pay attention to the distance from the spot face. This is not bad at all, but I want to align these two cavities. Center to center is always better. I will just move my drill slightly down by 1 millimeter. In this case, I'm touching the chamfer, so let me edit the spot face depth. Let's make it 2 millimeter. And this is good. I want also to reduce the drill depth of my. Now, these drills are touching. This is a mistake. It will be highlighted by connection check. I don't need to run connection check. I really can solve the problem on my own. I will add the material. I put a cutting plane here and add 10 millimeter. And I'll move my drills to the left. And I'll also stretch a bit this drill so that the connection will be better. So I've made the tank connection, and let me just incline a bit more. I need to rush a bit, otherwise I'll don't have enough time to finish the other elements. So that's good. I need the LS, so I'll put my shuttle valve, and I'll put my LS port, which will be maybe on the back face. I can align these two cavities. I'll need to move slightly my cavity here. I'll connect two ports. So one LS is coming from the flow regulator, so I'll add a construction port here on this side and stretch it. And the other LS is coming from the working elements, so I'll add a construction port here, a small one. I put it here. I stretch my drill up to the LS. I copy the same plug position here and connect to both cavities in the center. Now this drill is too close. We can match properties, copy this drill with the other one, copying the same alpha and beta, same inclination, so they get the same direction, and now the plug will have no issues. Let's verify the connections in our block. There are some mistakes. So here we have introduced the problem. There is an intersection here. So that's a mistake. We need to add more material. And now I really need to get rid of this inclined plug, and I need to add a couple of plugs. Let me add some material on the length. 10 millimeters should be enough. I'll stretch my drill and I get back to the original 10 millimeter diameter. So now I copy the construction port here, connecting to the port, and similarly I do again copy and position here, connecting to the two ports. Now it looks better. Let's do again a connection check on our block, and there are no major issues. So there are some dead area working area intersection. I show you a couple of so I'm using precision 0, so sometimes with precision 0 it means no decimal places in the position of cavities. There can be some intersection with the dead area. This is really not a critical item. There is another one here. I'm just going through a bit of thread, not a problem at all. This one is a problem, and I'll just make a connection, which is better. Let me stop with the custom inlet. So I'll just fix a bit of engravings. I don't need the engraving on the right side, and the other engraving look okay. Let me save my block. Now I go to the assembly and verify that everything, that my system is working okay. So I'll do a new assembly. Sorry, it went on the other screen. New assembly. And I'll do an automatic assembly of my block. Now all the elements are coming automatically, all except the working sections, because they were not linked in my hydro diagram. Well, the block looks good. I just do manually place my Bosch Rexot element and also my Eurofluid subplate. I'll also add the end plate standard end plate for Eurofluid. So I tried now to mate. This face will go here. So in this case, I'm not using MDTools assembly rules, so I just need to assemble manually with inventor commands. So if you have a 3D mouse, that will be very handy. And this one will be here, and I just do mating with a face. Looks good. Let me just do a pattern. Let's say 46 is the distance on the other direction, and I need 4 elements. And similarly, well, let me add a Bosch Rexroth 4W6J. Well, anyone will work. HJ6X, this one, and I'll mate it as well. And I'll do also a pattern for these two. And those are 48 millimeters, and I need 3 of them. And I also assemble the end plate. Of course, I will need tie rods, but that's not now the case for tie rods. So I want to make the end plate. Let me save my sectional valve assembly. I want to build the end plate for the working elements. So I'll get back to my, well, I need a new part. And I need, of course, my small block. The end plate will not be that big. If we go back to the diagram, I had sketched it. The end plate had just a tank port, and the P and LS were plugged. So we go and make a small end plate. It will be 65 by, let's make it 20 by 65, a small plate. What we can do is we can mirror the footprint that we have in the block. So we can use a command that is called mirror footprint. We take the main footprint. We want to mirror with the drill from both ends with counterbore, and we select the bolt holes. Well, sorry, it's the folder is true bolt holes, and it's TCAM8. We can also select the O-ring, so we can put O-ring with counterbore, and we can select directly the O-ring groove. I'll show how to manage O-ring grooves in the dedicated webinar to the tools library manager. So I just select random ones. I'm not sure they are the correct one for this element, but later we will be able to change them. Okay, now we go back to the our subplate and position it. So this command will create a mirror footprint. Bosch Rexroth will create a mirror footprint. Oh, now it's not working. That's unexpected. Let me do again. Maybe the block was not large enough. That's possible. Mirror footprint. Otherwise, I'll add. Well, let me skip the O-rings. I'll add later with counterbores. Okay, and we get back here. Yes, the reason was the size of the block. Later we'll be able to change it. Color. So this is really our plate. This is not needed. Also the LS will be very short, while we'll need a tank port. The tank port was a G1/2. That's our tank port, and we position it somewhere here. And we can reduce the drill depth. That's okay. We can add O-rings. So now I do manually O-ring groove for this drill. This was, let's see, counter bore 0.13. And similarly, maybe it's a groove. I selected a counter bore, but you can define if you want an O-ring groove or a counter bore. Let me take a groove. And also here, let's use a groove 0.14, and also here we'll take a groove that should be greater than 4. This one should be okay. That's our end plate. So let me save it as an end plate. Well, of course, we could reduce the size of this, so we can just stretch to 35 and maybe less. Let me put the cutting plane on the width. Here we remove other 5mm, but this is not really relevant. Save, and we go back to our sectional valve assembly, and we place now our end plate, which we want to assemble. Constrain face to face, and bolt with bolts. Of course, we can later add the tie rods and so on. So our system is ready. We still have a couple of minutes left, so we'll take a look at the machining drawing for the block. So let me go to new standard drawing. If you have questions, feel free to post in the question. So let me create a new drawing. I'll create the views of my block. So I'll take my custom inlet. You can define the projection type and the scale. And highlight construction plugs and engrave the text. Show the footprint and the port application names with the naming. So in this case, we have a PT, and for the PTLS. If you need to change the position, you'll need to double click and just drag. So all the text in the face are added into one sketch in Inventor, while in SolidWorks they are free to move on their own. In Inventor, you'll need to edit the sketch and then finish the sketch to consolidate the position. We can add origin and axis to our drawing, auto dimensions, and I usually add the machining callouts. Well, in this case, the auto dimension are only for the parent cavity of the footprint. If you want to put the dimension for all the elements of a footprint, auto dimension, configure, dimension each cavity in a footprint. So we do again now, there will be a X and Y position for all the drills. Now what we need to do is just move in the text all around. There is an easy way to align all the text on the left or right. You just select all them and do a right click, align vertically and or horizontally. This will work in both ways. So in this case, I want to align horizontally, and then you can move them all together and change the position. So this is the easiest way to make adjustment to machining callout position. So our time is over. Just the last information, if you want to play a bit with the sectional valves, remember we have a sectional valve configurator in NetScheme. Let me see if I'm netscheme.com. So in my case, my exercise, as I have made my elements in manually with HydroCAD, but we have a sectional valve configurator in NetScheme that allows you to create sectional valve diagrams very quickly into our cloud application. So if you don't have an account, feel free to sign up for free for a 30 days trial. And here there is NetScheme is a cloud application for circuit diagrams where you have the ability to draw all sorts of hydraulic schematics, industrial, mobile, and we have this, which is our sectional valve configurator. It's a growing library, so now we have some manufacturer, and you will be able to create sectional valve assemblies for various manufacturers. This is compatible with HydroCAD, so anything you do here will be a DWG, which can be then brought into Hydro and edited as well. You will be able to edit spool type, body, and auxiliary block in case this is a heavy sectional valve. By the way, we are running out of time, so I turn it over to Frank. And thank you for the attention today.
All righty, thanks, Carlo. That is all the time we've got today. So if you guys have any follow-up questions after the webinar, you can send us an alert email to support@vestusa.com, and we will try to follow up with you within 24 hours. I would like to thank Carlo again for delivering today's product application demonstration. We'd be grateful if you can complete a short survey at the conclusion of today's webinar. Also, tomorrow you'll receive an email containing a link to view a replay of today's session. Feel free to share this link with your colleagues. A link to view video segments from prior webinars will also be provided in that email. As you can see, we have the webinar series posted on various social media channels. We invite you to follow these channels so you can receive the latest updates on our upcoming webinars as well as any product releases. Our next webinar is scheduled to occur Tuesday, January 25th, where HydroCAD sheet set management will be demonstrated. Thanks again, Carlo, and thanks to everyone for attending today's session. Have a pleasant and safe day.